volcanoes put CO2 out all on their own. It's the second most abundant gas they put out. But these volcanoes were also burning through basically one of the world's largest coal basins in Russia. And we're just igniting, limestone, natural gas, coal, anything they could touch, and injected something like, the estimates can be a little insane. Some of them are like tens of thousands, or like 30,000 gigatons of CO2. The highest one I've seen is 120,000 gigatons of CO2.
And for comparison, how much do humans put in every year?
Yeah, so every year we put 40 every year. And I think we've put, is it one or two? I know if we burned it all, sort of all economical fossil fuels, it would be 5,000 gigatons.
Okay.
So this would be like, we burn all the fossil fuels, and then for some reason we just start burning limestone for fun on a continental scale, and we do it for thousands of years.
Welcome back to Decouple. Today I'm joined by Peter Brannen, who is a science journalist, author of Ends of the World. And Peter, I believe you have an upcoming book. I came across your work on our mutual friends podcast, Nate Hagens, and decided I had to have you on. So welcome aboard, and fill in the bio a little bit. Tell us a little bit more about yourself.
Yeah, my name is Peter Brannen, and I'm a science journalist who's been writing about earth science now for over a decade. And I really got into, this geological wormhole that I've been writing about for, the last 7 or 8 years, sort of through an unexpected avenue where I was writing a lot about ocean science and climate science. And then I realized that sort of half the story with climate change, at least that as far as I could perceive, was that, we have climate change modeled, and it's very theoretical and it's in the future. And that's half the discussion. But we actually have this experimental record of climate change. The only way the Earth has actually ever responded to, huge pulses of CO2 into the air is in the fossil record. And we test models for the future on their ability to reproduce some of these events. And sometimes they can't, sometimes they can. And so I just thought that was sort of a huge undertold part of the climate story, is sort of its legacy in the fossil record. And I guess sort of the scary part, or the punchline, however you want to phrase it, is that sometimes when experiments that look very similar to the one we're doing now, different in important ways, have been run on the planet in its past, where giant pulses of CO2 go into the air over the course of a few millennia, you see all the sorts of things that we're worried about in our own future. And in the most extreme cases, you get these big, nasty mass extinctions. So everyone's familiar with the mass extinction where the big dinosaurs went out, got wiped out. And, that one is very much associated with an asteroid impact for good reason. There might be some other stuff going on there that we can get into. But it turns out that's, by some accounts, the fourth biggest mass extinction in Earth history. And there are 4 before it, some of them which are hundreds of millions of years older. And for the most part, asteroids don't explain those. You can't find convincing evidence for asteroids at any of the other big mass extinctions. And instead, what you do find is these sort of mind-bending volcanic events where thousands of gigatons of CO2 comes out of the air. And if you know how to read the rocks, if you're a clever geochemist, you can analyze the fossil record and tease out what happened to the planet, how it responded to these big, crazy injections of carbon into the air and atmosphere. And so I thought that was a big story that was sort of undercovered, and I've made it kind of my niche, not quite aware the learning curve I would have to ascend to just geology. There's so much jargon, and it's such an interdisciplinary thing where you have to understand the ocean and the atmosphere. And in the case of dinosaurs, even stuff from outer space, you need to know how to interpret that in the rock record. So I have just gone down this wormhole in the last few years where I sort of only look at what we're doing today from the context of deep time and what lessons we can draw out of Earth history and what they can teach us about our future.
Yeah, it's interesting in the kind of energy planning world as well. So much depends looking forward on modeling. And I'm blanking on the guy's first name. It's, I think, Edward Bok's famous statistician. All models are wrong. Some are useful.
Yeah, right.
And obviously, looking back in time in terms of, energy transitions or so-called energy transitions, that's certainly useful. You can draw lessons, and they, may or may not be applicable to the future. So I'm seeing lots of overlap there in terms of, the two areas that we're studying. Reading your book, I was struck with, the kind of kill mechanisms of the mass extinctions. which again we're going to get into in a little bit more detail. But just how this incredibly powerful fire ape species is essentially capable of mimicking so many of those. And even if you think about an asteroid strike, global nuclear exchange with ensuing nuclear winter might mimic that fairly well. I imagine, there's no bomb, no single bomb that can produce anything like it. But maybe if we kind of set everything off, which is not unfeasible, and similarly kind of changes in CO2, and we're going to get into a little bit, I think, the kind of eutrophication or kind of overnourishment of the ocean. So maybe let's get into that by walking through a few of these events. I know a couple of them are kind of relying on the same mechanism. So maybe let's kind of take it mechanistically or chronologically or however you like.
Well, there's the first four all have to do with huge derangements of the carbon cycle, basically, through these kill mechanisms that are intrinsic to the Earth itself. Two of them are caused by these just mind-bending volcanoes. But the first two are a little odd. So if I can do it chronologically, if you want, I can kind of
actually. But before you do, let's just nerd out a little bit on this concept of geologic deep time, because it is so mind-bending. I think there's probably only physicists, astrophysicists, and geologists that really kind of get into this. I mean, of course, human beings go down to like the nano level, so there's all sorts of things that our brains are not designed to do, but in very modern times we've become capable of. But like even just establish a timeline to fit this into. So Big Bang is 13.8 billion. Key events along the way. Earth forms.
Earth forms about 4.5 billion years ago.
Life emerges.
Life emerges maybe around 4 billion years ago. I get into that in my next book, actually, because it turns out that's sort of a carbon dioxide story too.
Oh wow! Okay.
Life emerges maybe 3.8 billion years ago.
Great oxygenation event.
Great oxygenation event happens around 2.4 billion years ago.
And is that a mass extinction, or there just wasn't enough biodiversity to call it that?
Yeah, so I don't if you talk to people who actually work on that time period, there is this pop science idea that it was like, oh, this is actually the biggest mass extinction. And people have said that to me. But if anything, it's an expansion of the biosphere because you don't lose anoxic bacteria. Like there's still major parts of geochemical cycles today. You just get this new expansion of aerobic life. And then actually it's at the end of the great oxygenation event that you have this massive crash in oxygen after a few 100 million years, that then you see one of the biggest, it's very clear that the biosphere shrinks dramatically. And then you're at pretty low oxygen for another billion years or so until you go into this episode of Snowball Earth, which is another thing I'm really getting into now, especially in my next book, which might have been caused by a decline in CO2 from the breakup of a supercontinent and weathering of the continents. So today we are investigating weathering rocks, things like basalt, to sequester CO2. That's like one of our tools. And it turns out the Earth also does that on its own. And it's the most effective way of sort of burying carbon over the long term is weathering rocks. And you might have had this really accelerated pulse of it that throws you into Snowball Earth. There's other, proposals for why you go into Snowball Earth. But then for some reason, you have the biggest climate catastrophe in Earth history. And right after that, or not right after that, but in the wake of that, you get the emergence of large, complex, multicellular life, and then the explosion of animals in the Cambrian. So you go from this period of 4 billion years without complex life, this massive episode of just completely unimaginable climate chaos. And then out of it, you get sort of the champagne cork is popped and animal life comes out. So there's people investigating what the relationship is between those two things. And, NASA underwrites a lot of the research because if that has something to do with the emergence of life here, then maybe it does on other planets too. But yeah, I just said that all in a paragraph, which makes it sound like it didn't take that long. But the tool that I use to think about deep time that I also ran through in Nate's podcast and that I use in the book as well, just because I find it so useful. There's a lot of ways of thinking about this. One paleontologist showed me a beer and he said, oh, just like the foamy head on the top, that's all of animal life. But
wow, I like that.
So the other one is you hold your arms out at so your wingspan is fully extended. And John McPhee, who is this New Yorker writer who wrote about geology, said if you took a file, like a nail file, and filed off a little bit of one of your fingernails, that would be all of human history or something like that. So that's a way to think about it. The one I like is that if you imagine every footstep you take is 100 years back, and you go for a walk, within a few footsteps, it's the Roman Empire, and 60 footsteps after that is the beginning of recorded history. And then, I don't know, 200 footsteps after that. So you've barely walked out of your house, and sea level's 400 feet lower, and there's camels and lions in North America, and there's an Antarctica's worth of ice on North America. And, the world is totally transformed, and you've walked a couple hundred footsteps. And then you ask, how much further would you have to walk to the beginning of Earth history? And, you might think it's a couple miles to the dinosaurs and the trilobites, but you'll be at the origins by sunset or something on this walk. But you'd actually have to walk for 20 miles a day for almost 4 years to cover the whole history. And so another reason why I think thinking about what we're doing on the planet today in this context is that these sorts of climate perturbations and carbon cycle perturbations that we're seeing in the last 200 years, you really have to travel pretty far back on this walk through Earth history to find anything comparable to at least the rate of change that we're driving on the planet now. So that's why I think it's so important. You can't really understand how radical the experiment we're running on the climate is unless you put it in this deeper time context and realize how out of equilibrium the global industrial experiment on the planet is.
Right. So, like the Holocene has been this great sort of period of stability in which human agriculture has emerged, and in our historic memory anyway, and of course the great advances in human well-being, I guess, with the Industrial Revolution. Is there something kind of similar at play in terms of the emergence of multicellular life in the Cambrian explosion? That Earth's chemistry kind of stabilized such that life with all these pulses of extinction and radiation could occur? Like, was the atmosphere just like ridiculously different? Or I guess it's hard to have life under a snowball or like global glaciation.
Yeah.
But
Well, the Earth has this dramatic thaw after Snowball Earth that's almost hard to describe. People talk about the freeze, and not people, geologists do. I don't know how much people are talking about Snowball Earth, but the way the Earth escaped from that, basically, death sentence of being completely locked in ice, was that the whole world was encased in ice. Possibly there might have been some open water at the tropics, that's debated, but none of the CO2 was getting. So you don't have much photosynthesis, you don't have much rock weathering because everything's covered in ice, so you're not burying any CO2, but there's still volcanoes poking up above the ice, putting it up into the atmosphere. And so you suddenly rapidly melt out of Snowball Earth because CO2's gotten to this threshold where it's not getting removed from the atmosphere, but it keeps getting added, where it might have gotten up to something like 100,000 parts per million or something totally mind-blowing. And then the planet flips and you go into, the whole thing melts in the matter of a couple of millennia, and the ocean's covered in a mile deep, like freshwater lid that's 150 degrees Fahrenheit of water. So it's just like this completely crazy thing. Eventually things even out, and then you get these sort of blob jellyfish sort of world called the Ediacaran, but that's not the Cambrian yet. And those might not even be animals. They're just sort of these weird experiments in multicellular life. And then you do get this explosion of complex life where things develop shells and start developing eyes and start hunting, and there's that arms race and all this stuff. And I do view sort of what we're doing today is maybe analogous to that. It might have been the rise in oxygen, or it might have been an influx of food that powered this explosion of sort of biotechnology. And it wiped out this world that existed before. This sort of placid jellyfish world, or jelly world, got wiped out by this insane burst of energy and biological innovation. I mean, that's sort of the best case scenario for us, is that we are at the dawn of sort of a new Cambrian, and the Earth's not going to look the same after this. And we'll learn to live in sort of something that makes sense in a long-term perspective. Like, the birth of animal life was a good thing. Or the alternative, the much worse option, is that we more resemble one of these big volcanic events that I mentioned, where it's just this burst of energy and CO2, and we wipe ourselves out pretty quickly. So I think those are the two kind of options if we have precedents in Earth history for for what we're doing, and we have to kind of choose which way we're going to go. Are we going to be a sustainable phenomenon on the planet, or are we just going to burn ourselves out?
Right. Well, let's walk through the more recent mass extinctions you mentioned. And again, I think the mechanisms are really kind of what interests me. Although I'm sure there's lots of fun little kind of details and little side tangents. I love those too. So because I think that the eutrophication one was really interesting, but I think the first one, if I studied your book well enough, and Ordovician, CO2 actually goes really low. So yeah, just walk us through that, because that actually, I guess, talks about some of the potential kind of regeneration of the planet in terms of going down on CO2, if I'm not incorrect.
Yeah. So this is after the Cambrian, like 100 million years or so after the Cambrian explosion. So animal life is trying to find a footing. It's still a totally alien planet. Pangea is hundreds of millions of years in the future. It's the continents haven't come together yet to make Pangea. There's not really any life on land. There might be some tiny little unrecognizable plants sort of at the edge of at water's edge, but in the oceans, you do have this really vibrant world of things that look like horseshoe crabs and these big squid with cone shells and stuff like that. It's a pretty alien world, but life is doing really well right leading up to this extinction, and then it just gets 85% of species go extinct at this extinction, or 80 or something like that. And there's evidence for this massive ice age at the end of the Ordovician, and there's all sorts of evidence. You can see geochemically, you can tease out signals of the temperature dropping, but you can also see, scratch marks from glaciers in the middle of the Sahara Desert today that are from this extinction almost a 500 million years ago. Africa was over the South Pole at the time. There's similar features in Saudi Arabia and things. And, whenever I see oil geology reports, I'm always, I'm the one nerding out about they'll say, oh, it's the Ordovician Silurian boundary. I'm like, oh, that was the big extinction. But yeah, so why did the Earth? So you go into this ice age, sea level drops by a ton, you lose all the shallow habitat where all these animals are living, and the circulation of the ocean changes, which changes the oxygenation. And the cause that, in writing this book, I sort of had to find where the consensus was heading. And what most researchers were talking about was the weathering of the early Appalachian Mountains, which were just forming over the tropics. And if you build mountains in the tropics, it's a really effective way, because there's lots of storms and weather there, to weather rocks, which is just what it sounds like. It's weather reacting with rocks and breaking them down. And weathering is one of the most effective ways of sequestering CO2. So you have this pulse of mountain building that's sequestering CO2. You finally pass this threshold where sea level, the ice suddenly forms on Africa, sea level drops by hundreds of feet, and all this stuff gets wiped out. So that's kind of a weird one, but it does sort of have some relevance to today, just because it has, rock weathering is something we're interested in now.
In terms of geoengineering.
Yeah. And it shows you that thresholds, we're worried about the temperature going up too high, but there's also, this is a case where you pass a threshold and, it drops too low and things totally change. Because in Earth history, we look at these plots of temperature and CO2 to like 2100, and we have this idea that everything's just very linear. And for the most part in Earth history, the changes have been, kind of step changes, threshold sort of changes. And so that seems like that's what was going on here.
Do you think that like linear extrapolation, is that just like the kind of most locked in simplistic way of like human prediction? Like we do that everywhere. Unless we kind of activate that sort of systems two thinking and try and like reason and logic through and apply, previous lessons. But it's just, I don't know, it's just wild to me that that's kind of the basic mathematical function that, our brains default to.
Yeah. I mean, I think those models are like very well supported, and maybe it's 2100. That is how the Earth will respond. But I also think when I see, especially when it's like, here's what our emissions are going to look like, they provide this sort of, I remember one that got sort of circulated among very reputable scientists where it literally was outside of the range of uncertainty within the first year, and it went to 2100. And so I don't know how, I think the future is a lot more open-ended than we tend to give it credit for. And they sort of give us this false sense of security that we're in good control of this stuff. But yeah, I mean, the lesson in Earth history is that the Earth sometimes responds very unpredictably in some really dramatic ways. And the more you push on a system, that sort of further out of equilibrium you push it, the more unexpected surprises you're going to get. And I think Earth history teaches that lesson.
Okay, let's jump into the next
Yeah.
kill mechanism, and this is similar to. I mean, again, in my framing of like humans are activating a number of these mechanisms. This is kind of like the agricultural revolution or something, or chemical agriculture.
Yeah. No, the next one I also think is kind of a optimistic analogy, like the Cambrian, for us in the future. So the second mass extinction is this thing called the end or the late Devonian extinction, where you have about 25 million years of pulses of mass extinction, including two really big ones. And a signature you see all over the planet are these black shales everywhere. These are a lot of the black shales that we frack today. So like the Marcellus and the Brannen and the Barnett are all from the Devonian. They're all from these pulses of mass extinction. When you see black shales, it means that the body of water where that rock was left behind was anoxic. There's no oxygen, and because all the life in it died and fell to the bottom of the sea and never got respired or eaten, so it just stayed there. And so those are juicy rocks to frack and things today. And so the Devonian, it seems like the ocean's repeatedly losing its oxygen and leaving behind all these black shales in the rock record. And the sort of, again, the consensus kill mechanism for this one is a very strange one, but this is sort of the dawn of the land ecosystem. This is when those little sort of pathetic plants are on water's edge that I mentioned last time suddenly explode into trees and forests. And over the course of tens of millions of years, have these repeated biological innovations like seeds and roots that allow them to push further inland. And as they do so, they are sort of breaking up this continental rock for the first time, releasing all these nutrients like phosphorus, which we put on our crops, that washes into the rivers and then out into the ocean, and it's fueling these huge algae blooms. And when algae blooms die, they get eaten by microbes, and they use up all the oxygen in the water column, and so you starve everything in the ocean of oxygen. And we actually see something similar today. And it's not because of the evolution of trees. It's because we mine phosphate rock in Morocco when we spread it in the Midwest, and it washes into the Mississippi. And so seasonally, every summer, the Gulf of Mexico loses or has an anoxic zone that's something like the size of New Jersey at its biggest, and it causes fish kills and is bad for fishermen, and everyone hates it. But you saw something similar in the Devonian. Only it was caused by the geoengineering of the planet by plants. The same time, trees sequester a lot of CO2. We use these, we're looking for, some people propose them as ways to sequester CO2 in the future, is, plant a bunch of trees. I don't know how likely that is, but you also have this evidence for ice ages in the Devonian as well, which might be caused by this forest planet sort of sequestering so much CO2 that it is both eutrophying the ocean and dropping it into these ice ages. So the reason why I said this might be sort of a positive or like a role model for us is that trees went on to underwrite the flourishing of the whole biosphere, and eventually they found their equilibrium with the planet. And but their introduction to the ancient world was really pretty catastrophic. And the things they wiped out were, I get into in the book, but these incredibly terrifying fish that were, I say in the book, they were the size of buses. Unfortunately, recently they have downgraded their size and they made them look less cool. But if people are from Cleveland or have been to a natural history museum and they see these gigantic, scary fish with like guillotine blade mouths, that's usually Dunkleosteus. And those are found in the Cleveland area and all over the world, and they get wiped out in this extinction. And reefs go almost completely extinct as well. So that's number 2.
All right. Number 3 and 4, similar mechanism. So let's jump into that. This is crazy.
Yes, and sorry I'm taking so long, and that I went into that tangent about Snowball Earth. That's just because that's what I'm working on now.
Okay, just kind of tangent. I'm going to meet your tangent with another tangent. So I briefly studied glacial geology, and before that, I'd been a mountain man, actually guiding hunts in the Yukon. And so my professor was hiring a logistician for a geologic expedition to look at the Toby Formation in Western Canada. And my marks weren't great in geology, but I had the most credibility in terms of like fending off grizzly bears. And we were going into the Purcells, this mountain range. And I had to overlay geologic maps, the topographic maps, and figure out, plan routes to where this formation was. Cause it was Toby Formation. I think it's like almost a billion years old. Anyway, and what we were looking for was drop stones. So, when a glacier picks up some stones and goes over water,
Yeah.
those stones fall out and they leave a particular mark in the sediments. And it was just like insane looking at these near billion-year-old rocks for these
Yeah.
impressions of stones that had fallen off a glacier to try and confirm Snowball Earth. So anyway, I've got this tie-in. So I've got all the time in the world for Snowball Earth, but
I have another tangent there, but I'll restrain myself.
Okay, maybe we'll get into it after.
Right.
Okay. For the listener's sake, let's talk about big ass volcanic eruptions.
Okay, yeah. So the third mass extinction is the end Permian mass extinction. It's 252 million years ago. So the first two were at 445 and 375, and then there's one at 359 too, that I sort of included in my last discussion. But the next one is at 252 million years ago, the end Permian. It's by far the biggest mass extinction on Earth, and it's number one with a bullet. It's way bigger than any of the others. It almost needs its own category. You do have an ecosystem's up and running on land, so you have trees and big lumbering reptile sort of things, but dinosaurs are still tens of millions of years in the future. They come after this extinction. You have things that look like reptiles that are actually more closely related to us. So it's funny that there's sort of this trope that mammals didn't really get their shot at the top until after the dinosaurs go extinct hundreds of millions of years in the future of this extinction. But that's actually, our line actually dominated the terrestrial ecosystems at first. They weren't quite mammals yet. They were still but they had branched off from reptiles already. And some of these were really scary looking things. There were the gorgonopsids, which were the top predators, some of which had teeth that were longer than T-Rex teeth. They're sort of like they're like very agile, athletic looking animals. They all get totally wiped out. In the ocean, reefs have bounced back by this time. A good place to see what a Permian reef looks like is at the Permian Basin Petroleum Museum in Midland, Texas, where they have a great diorama, because the Permian was an incredibly prolific oil producing time, especially in Texas. But then at the end of this extinction, reefs get totally wiped out. It takes tens of millions of years for them to recover. What's really eerie in the oceans is that your listeners might be familiar with these things called stromatolites, which are sort of, you might know about them from the Precambrian, these mounds of bacterial slime that cyanobacteria make, that some people point to as sort of the first fossil life in the fossil record. They disappear completely for the most part in the age of animal life, because once the seabed has animals burrowing and stuff, you can't grow these like microbial mats. Except for in the wake of the Permian mass extinction, you see them sort of come back all over the planet, and it's because animal life gets so wiped out. Insects take a hit, and they're only, the only mass extinction that really affects insects. You see these weird, evidence that things have gone really wrong. There's this thing called the fungal spike, which is sort of in strata of the extinction all over the world. That people think might just be, some people think it might just be from like things rotting and fungus kind of taking over the planet. So it's really gnarly, and it takes about 10 million years for the planet to recover. And because this one was so extreme, and because the asteroid had already been sort of validated as an extinction mechanism, people sort of scoured the planet looking for an evidence for an asteroid impact at this event. And there isn't any convincing evidence for an asteroid impact, but instead, there's this massive area of Siberia called the Siberian Traps, which were these lava flows that erupted on like a continental scale, and they're dated, precisely to the mass extinction. And to give you some scale of what these volcanoes actually were like, so they're not like, it's not Mount Fuji or anything like that. It's more like Iceland would be a good way to think about it, where it's sort of this burbling fissure eruptions just happening over a whole continent. But enough, the magma and lava that's associated with the Siberian Traps is enough to cover the United States a kilometer deep in lava. So not even like in inches of ash. We're talking, that's the lava part.
Right.
So that obviously is very extreme. And the fact that it happens at the same time as the extinction is, pretty telling. And they would have been putting out all sorts of bad stuff, like stuff you'd have in a World War I battlefield. Like there would have been chlorine gas and mercury would have been coming out of the volcano. So you might have had mercury poisoning and sulfur dioxide and things that would have destroyed the ozone layer. But by far, the biggest signature you see from these eruptions is a massive spike in warming and a massive sort of derangement of the carbon cycle, because they were putting out so much CO2. Volcanoes put CO2 out all on their own. It's the second most abundant gas they put out. But these volcanoes were also burning through basically one of the world's largest coal basins in Russia. And we're just igniting, limestone, natural gas, coal, anything they could touch, and injected something like, the estimates can be a little insane. Some of them are like tens of thousands, or like 30,000 gigatons of CO2. The highest one I've seen is 120,000 gigatons of
And
CO2.
for comparison, how much do humans put in every year?
Yeah, so every year we put 40 every year. And I think we've put, is it one or two? I know if we burned it all, sort of all economical fossil fuels, it would be 5,000 gigatons.
Okay.
So this would be like, we burn all the fossil fuels, and then for some reason we just start burning limestone for fun on a like continental scale, and we do it for thousands of years.
Right.
But I guess the reason why it's even relevant to talk about this thing in the same conversation as what humans are doing is that this happened over the course of something like 30,000 years. And as best as we can tell, we are the rate is faster today. And for things like ocean acidification, the rate is actually what matters. If you put a lot of CO2 into the air over a long time span, the planet has ways of scrubbing it from the system. But what we're doing is jackknifing so extremely that we can actually reproduce some of the effects of these extinctions. So like ocean's gotten 30% more acidic since the Industrial Revolution. If you project that into the future, you start matching some of these crazy geological events pretty quickly. And RCP 8.5, 3 centuries from now, we're not going to do it, but I think that's projected like 10 or 12 degrees of warming. And our best estimates for then Permian mass extinction is 10 degrees of warming. So the fact that we could even like reproduce what it took an entire continent of volcanoes to do is really kind of mind-bending. And the scary thing is, this is sort of what happens when you turn it all up to 11? What does the Earth look like? And it's the worst thing that's ever happened. The oceans lose all their oxygen, or not all, they lose about 50% of their oxygen. It gets 10 degrees warmer, you acidify the oceans, and basically the fossil record doesn't recover for 10 million years. So that's sort of like worst case scenario. We know what that looks like in the fossil record.
That stat about acid levels rising 30% in the oceans is pretty wild. It was higher in the Permian, and were there no fossils they're forming, A, because there was no creatures around, and B, because they just couldn't form shells, or what's the
so the role of acidification in the extinction is like I went to a geologist's office, and he showed me he had this chunk of limestone from China that he had sort of chiseled out and had polished that covers the extinction layers. And you see this like very shell-rich, happy world at the bottom part of it. And then there's sort of this like uneven surface that looks like it was sort of etched into it. And then you have this like boring muck on top of it. And he thinks that's evidence for acidification. It's very hard reconstructing what actually, like, we have a few layers and we have them bounded in time by a few tens of thousands of years. And we know everything goes haywire, and teasing out what is the actual kill mechanism and is difficult. But certainly there would have been massive acidification, and you do see things like reefs get totally pummeled. But what's kind of crazy though is like the planet overcorrects so much in the wake of this that then you have just torrents of weathering on land because it's super hot and there's tons of storms. That then you just flood the oceans with alkalinity. So after the like warming acidification part, you get these just crystal fans of aragonite on the seafloor that is just like calcium carbonate crashing out of the ocean in the wake of it. So it takes a while for the planet to sort of come back from this crazy seesawing after the extinction.
It's wild because, I think most of what we hear about are positive feedback mechanisms for climate change right now. And I guess as you move out centuries or millennia, that was interesting. Just like the ferocity of storms interacting with rock speeds up weathering. I'm a medical doctor, so I'm just thinking about like homeostasis is my kind of frame with which to understand this. Now the Gaia hypothesis is out there suggesting that this is all one big integrated system, that life kind of sustains itself by creating the circumstances in which it can live and thrive. But what you're saying is these are violent swings. This isn't just getting a mild fever and returning to normal in a few days by shifting a couple degrees. Yeah.
that might be what does it. Maybe it's not the warming. Maybe it's the extreme swings faster than life can adapt to. But yeah, there are interesting feedbacks. Like one result of the ocean losing its oxygen is that it gets a lot easier to bury carbon in it, which cools the planet again. So there are these weird feedbacks. And if sea level goes higher, you have more space to bury the carbon, and that can cool you off. And so there's all sorts of weird counteracting
And like when
feedbacks.
you talk about extinction, right? Like if like a fraction of a percentage of a species endures, then they didn't go extinct. Like, are we
Yeah,
talking like just in terms of, I don't know, biomass or the amount of life dropping? Like we at a mass extinction, that's a certain percentage of species going extinct. But what does that actually look like in terms of like I don't know, the biomass of creatures pre and post? Or do we have a
that's a
sense
good
of that?
question. The fossil layers immediately after the mass or the end Permian look pretty like eerily kind of vacant. You might find this like really weedy clam that's the same species of clam on the other side of the planet. It's just these monoculture weedy species. But it does, it seems like there's a pretty big drop in biomass, or it just reverts to like bacterial biomass.
Right, right. Oh,
Um,
interesting.
yeah, if you hear like, it might not sound that impressive. It sounds impressive 90% of species on Earth going extinct. But a species that survives might have 99% of its members wiped out and it still makes it through. To wipe out an entire species is really a pretty extreme thing. And to wipe out a family, so families of animals of life go extinct as well, which means that not only does every individual member in the species have to go extinct, but all the species in that family have to go extinct. And you have these huge chunks taken out of basically the tree of life, especially in the end of the
What's a
Permian.
contemporary example of a family, just for a frame of reference?
Okay, so yeah, like Canidae, the species that has like foxes and dogs and all that stuff. That's
A
a
family.
family.
Okay, got you.
Yeah,
Got you. All right.
and coyotes and all. Yeah.
Yeah, let's wrap up the last extinction and then get a bit meta.
Oh yeah. So we have two more actually, but I'll skip. I'll
Right,
kind of
right.
breeze through the next one because it's the same kill mechanism, just 50 million years later. You have this crocodilian world, and reefs kind of recover, but another one of these huge volcanic provinces erupts as Pangea is breaking apart. And what's incredible about this one, at least I think, is that if you go to New York City and you look across the Hudson at the New Jersey Palisades, those are like the Siberian traps. Those are remnants from these volcanic eruptions, and you can find the same sort of uh, that. Those are sort of sills of magma that fed the eruptions in New Jersey, but you can find similar volcanic rock dated to the same time period in Nova Scotia and Brazil and France and Morocco, all over the world. And it's from this thing called the end Triassic mass extinction, where as Pangea is rifting apart, you get this big volcanic province that covers 3 million square miles. It's absolutely gigantic. And it's only after the wake of that extinction that this sort of weird lineage of crocodilians sort of takes a backseat to the dinosaurs. And then you're in the happy days of the dinosaurs for 135 million years, until the big rock falls out of the sky. The weird thing about the dinosaur extinction, though, is that one too is associated with at the same time that the biggest rock to hit Earth in the last billion years, as far as we know of. The same time in India, there's another one of these continental flood basalt eruptions called the Deccan traps that weren't as big as the Siberian traps, but it was enough that it could cover the lower 48 United States in 600 feet deep of lava. So it's like it's no joke. And geologists are every field season are going out to try and tease out the relative timing of the asteroid impact in relation to these volcanoes and see, what the relationship is with the extinction. The craziest idea I heard is that these volcanoes were sort of humming along and weren't that important at all. And then when the asteroid hit, uh, it caused the equivalent of something like a 9 earthquake all over the planet and actually kicked these volcanoes in
Oh
overdrive.
wow,
And
yeah.
so it was sort of this 1-2 punch, but it's a very contentious field of study. Uh, I was lucky in that covering the earlier extinctions, sort of, you'll find someone at the end of a hallway in a university who no one ever asked them questions. So they're just delighted to talk to you about, the Devonian. But then you get to the dinosaur stuff and it's sexy and everyone wants to talk about it. So there people are kind of, it's very contentious. And I remember interviewing one guy who I told him I was writing a book about mass extinctions. And he said, I'm happy to talk to you about any of them except for the end Cretaceous mass extinction, the one that wiped out the dinosaurs. because it's too political and I don't want to like lose professional relationships. And I was like, wow, this is
You'd think
serious.
the carbon pulse ones would be the political ones because of the comparisons to the kill mechanism of today potentially. But contentious, I can imagine paleontologists throwing on their boxing gloves and.
Well, this is just the volcano and the asteroid people sort of put down roots in their camps like 2 decades ago, and some of them are still.
So in terms of the kind of in the very beginning when I was kind of making comparisons to the mighty power which humans wield, like how did that asteroid impact compare to nuclear bombs, for instance, or did you have any sense of that?
I think it was. I mean, it was way, 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 way bigger than. I think it was. So I have a line in my book, and I forget what the exact calculation is, but something like the Chicxulub impact was, I think, thousands of times bigger than if the USSR and the US had blown up all their nukes all at once at the height of the Cold War. So it was like way beyond human experience. But yeah, and I think some of the motivation, so there's this interesting sort of research braiding between the dinosaur extinction and the Manhattan Project. So Luis Alvarez was, with his son Walter, was one of the people who sort of wrote this famous paper in Science, drawing the connection between this layer of what was essentially asteroid dust and the end of the age of dinosaurs. And Luis Alvarez was in the Manhattan Project. He wrote a note that was dropped over Japan in the lead up to the atomic bombing, signed Luis Alvarez, telling them to surrender. And then his son was studying paleontology and was trying to tease out the answer to this one problem. And he says, well, I have some friends who are nuclear physicists. Why don't we put your rocks in the lab and we'll figure out, try to tease out some signals out of these rocks. And sort of had this gestalt moment where they're like, oh my God, it was like a nuclear war that killed the dinosaurs. It was this asteroid impact. So they do have this kind of weird relationship too.
And was it kind of a nuclear? I mean, obviously there's the impact, and I mean, I don't even want to talk locally because I imagine just the kind of thermal impact was not a small thing, but.
Oh my God. So, I mean, this is one of this event is one of those things that's like truly sublime and you can't even think about, you can't even picture it. So I remember asking one impact modeler, everyone knows those pictures where it's like, an iguanodon or a pterosaur looking over its shoulder as the asteroid hits. And I asked him, what would it look like to see the asteroid impact, from beyond the horizon? And he said the question didn't even make sense because if you're close enough to see it, you instantly would have just gone blind and set on fire because so much energy was released in the optical wavelengths that you couldn't see it. It was something you couldn't see. And it was, the size of Mount Everest. And it went from the cruising altitude of a 747 to the ground in 0.3 seconds. And the atmosphere didn't even make a scratch on it. Like it didn't even know it didn't know the atmosphere was there. It was just hit the earth and put a 20-mile deep hole that 3 minutes later was replaced by a 10-mile high mountain of molten granite. The whole thing is just completely unthinkable. But these effects after it, people have tried to, there are a few different kill mechanisms. One is that it just launched so much rock up into space that then took these sort of ballistic orbits around the planet. And when they re-entered, would have basically broiled the planet for 20 minutes. That is so extreme that even though it makes sort of sense in modeling,
well, it seems like broiling in an oven, just all these hot rocks in the atmosphere or in orbit.
Yeah, so this impact modeler who I talked to, Jay Malash, unfortunately he passed away a few years ago. He did these calculations and he was like, how much energy would this release? And he did an experiment on his oven. He's like, oh my God, it's the same as a broil on my oven for 20 minutes on the surface of the planet. A lot of people are skeptical of that because it might make sense, the calculations, but it's so extreme, it doesn't seem like anything should have survived that. Although it might be telling that things that burrowed kind of did pretty well. But things in fresh water did generally well in the extinction too. So there might have been longer term effects where just dust was kicked up into the atmosphere and shut down photosynthesis for a while. The asteroid hit a giant carbonate bank and would have injected something like 400 gigatons of CO2 into the air all at once by vaporizing it. It also put a lot of sulfur dioxide It might have acidified the ocean. So there's all sorts of different competing effects. We just know it was very bad. And what do you know? Like one of the biggest volcanic events at the same time is happening. So this kind of shows you. This is why I get like almost offended when I hear people like use dinosaurs as, oh, they were obsolete and don't be a dinosaur. It's like these things were dominated the planet for 135 million years. It took this level of absolute chaos to knock them off. They did nothing wrong. They were perfectly, adapted to their world and intelligent and capable animals. So
And again, sorry, I'm just trying to get my time space right, because that is an extraordinary long period of Earth history for like complex multicellular life. And the Cambrian explosion is like 500 million.
Cambrian explosion's like 510, 512.
Okay, so one fifth of
Cambrian's,
that time, dinosaurs are kicking ass.
I mean, if you look at it in terms of terrestrial life, you first get a terrestrial biosphere 380 million years ago. And dinosaurs, first of all, 245 million years ago. And today there's twice as many species of birds as there are mammals. So like, this is really that we live on a dinosaur planet. We're just here.
Wow. Very well adapted and weathering, I mean, it's wild that the Permian, I mean, you described some pretty incredible mechanisms, but that this asteroid impact wasn't more devastating than the Permian.
Yeah. I mean, that shows you how extreme the Permian is, that just through chemistry alone, things get so unpleasant that it kills more life than a crazy asteroid.
So I know your new book's, I think, dealing with carbon dioxide as its focus, and I don't want you to give too many spoilers. Maybe we'll have you back when that comes out. But I am interested because, this molecule is just such a potent regulator of planetary temperatures. We hear. Can you just get into like the basics of why that is? Why an extra few parts per million has such an impact?
I decided to write my next book, which is just about CO2. It sort of spun out of this last book, which is sort of the moral of the story was, here's what happens when lots of CO2 goes into the atmosphere or lots of it decline. Here's how it's this kill mechanism in Earth history. But in writing that book, I sort of had to reckon with and come to understand sort of that the geochemistry of this planet is sort of fundamentally modulated through CO2, basically. So all life is carbon. We know we're carbon-based life. And the source of that carbon is CO2. It enters the biosphere through photosynthesis or, weird hydrothermal vents. It's also CO2 based. It just uses a different energy source than the sun. But that's how CO2 enters the biosphere. And it sort of diffuses through the rest of the biosphere, and things eat things and they release CO2 back into the atmosphere. And there's sort of this huge interplay of the entire biosphere as CO2 moves around the planet. And at the same time, it is keeping the climate habitable. It is moving between the rocks and the air and the oceans and regulating the climate. And when it goes really out of whack, you have this thing called the carbon cycle, which is basically this whole story all integrated of CO2 moving between all these different reservoirs and somehow keeping the planet habitable, which is more miraculous than you might think. There was some throwaway line in a paper I read recently where it was something like if CO2 burial or release was offset by like 10%. So if you had over a long geological time span, within a million years or so, you either go into a Snowball Earth or like a Permian mass extinction. So we have this incredibly finely balanced sort of cycling of this one sort of crucial molecule. And so yeah, it's kind of miraculous that the reason why Earth is because of the behavior of this thing, the way it moves between the geosphere and the biosphere and the atmosphere. And it's important in the atmosphere because it is, water vapor is a stronger greenhouse gas. It traps more heat, but it cycles through the atmosphere really fast, whereas CO2 you put up there and it stays up, on a human timescale forever. And so water is really a feedback to however much CO2 is in the atmosphere. And CO2 actually blocks a different part of the spectrum that's not really covered by water. So that's why it's important. There's a paper that came out in Science, I don't know, 20 years ago called CO2 is the primary knob of Earth's temperature. And that's kind of the way to think about it.
So that's interesting. I mean, you've also kind of nerded out a little bit about just what life is in terms of a energy dissipating system, and obviously it's an energy dissipating system made out of carbon. But I'm wondering if you can go into that and get super meta and abstract for me.
Yeah. So yeah, in the discussion of sort of the origin of life in my next book, again, it's into some real heady stuff about sort of what is life doing. And there's some people who think about it sort of as, yeah, you have these. A planet has different ways of how do I even phrase this? Basically, okay. So let's start at the Big Bang. The universe started very out of equilibrium, and someday it's going to be in total thermal equilibrium.
Okay.
And basically everything interesting can happen between those 2 points as that uh, low entropy situation dissipates into a really high entropy uh, situation where you can't do any work again, nothing interesting can ever happen. That's like the heat death of the universe. But as it's dissipating, given that the things are only going to get more disordered over time, uh, things that accelerate that process might sort of be favored. And life is an incredibly good entropy generator. It builds these little islands of order by exporting entropy into the environment around it. And basically, to make anything ordered or interesting, you need to, you know, find disequilibriums and dissipate them so that you can do work on the environment. Uh, and so the planet, early in its history, might have been really frustrated chemically and thermally. Like you had these oceans that were way out of chemical equilibrium with the crust, and so you had these little like rockets of hydrothermal vents that were channeling this dissipation, that they found carbon chemistry through life as a mechanism to sort of dissipate this geochemical energy. Again, whenever I talk about this, I have no idea whether I'm making any sense
No, I
or
love
whether
it.
I'm
I love
blacking
it.
out or something.
Probably to a huge chunk of people, it makes zero sense. But to those of us
Yeah.
who like to nerd out on these topics, yeah.
Yeah, but there is this general trend over the entire history of life that's sort of curious. Where there's this guy at UC Davis, Gerard Vermeer. I think it's a Dutch name, so I'm not probably mispronouncing it. Whose whole thing is about how over the history of life, power in ecosystems and in organisms has sort of progressively ratcheted up. That there is this sort of stepwise change to higher and higher energy dissipation in the ecosystem. And so, I don't. I want to talk about the human story and the industrial revolution in this same story, but there's a risk of doing that and sort of naturalizing. Oh, see, this is just like nature running its course. And the last few centuries were pretty complicated, and there were humans doing bad things and stuff. But it is sort of eerie to me that it is at least in line with this broader trend over all of Earth history, where you find these larger and larger sources of free energy and get better and better at dissipating them to do work on the environment and making
Right.
these really ordered structures, whether they're organisms or societies or.
It feels a lot like a biophysical law, and fossil fuels feel a lot like steroids in terms of just
yeah, they're a PED. That's what they are.
Yeah, no doubt. Finally, I wanted to get into a little bit your expertise, prior and probably during, which helped a lot in terms of understanding more of these ocean-based worlds. Wanted to chat a little bit about the ocean because I've kind of neglected talking and covering that, and it does seem to be such a critical buffer. I think both in terms of slowing temperature rise and CO2. Can you give us a little explainer on that?
On
the kind of buffering effect for temperature and
oh yeah,
and CO2 absorption, things like that.
Yeah. So if the oceans weren't there, I think the temperature, if we had the Industrial Revolution until today and the oceans weren't there, I think temperature would have gone up over 100 degrees Fahrenheit already.
Wow.
So like 90% of the heat has gone into the oceans. The acidification is one sort of expression of the amount of CO2 that they've absorbed. They are this massive buffer that up until now has shielded us for the most part from the effects of what we're doing. But the more heat you jam down there, the more you're kind of playing with fire. But yeah, it's 3/4 of the planet. If you spin the Google Maps the right way, you can just see, the Pacific Ocean. It basically looks like the whole planet. So yeah, I mean, the oceans are kind of the regulator for the whole thing. I don't know if that answers your question, but yeah.
Yeah, and I mean,
and totally neglected. I totally agree. Like 90% of the large predators in the ocean have been taken out of the ocean in the last 50 or 60 years. They've already lost 2% of their oxygen since 1960, I believe, which 2% might not sound like much, but when you're talking about percentages of oxygen in the ocean, that like, again, you need these geological precedents to start being, having an analog. So we've done some really, it's out of sight and out of mind, so we don't really think about it too much. But yeah, the last few and it goes back centuries. This isn't just an industrial thing. Like there might have been right whales wiped out in Europe, 1,000 years ago, and even in the like pre-colonial Americas, you'll see localized instances of sort of fishing down the food chain when sort of big reef fish are taken first. And so, humans are have always been sort of the keystone species who have had these massive top-down effects on the environment. It's just now everything's so supercharged with all the power we have to change the environment.
And again, I think like it's fascinating hearing these numbers, like the asteroid impact, 400 gigatons, the Siberian traps, 100,000. I can't even remember the number, thousands of gigatons. And so it seems like the ocean would have a lot more capacity to buffer and absorb over longer time scales. Is that correct? Like, are we just heating up the top layer? And
so it started to make its way into the deep, but there's this paper that was a summary of sort of the carbon cycle that came out recently by Scott Denning, who's at CSU, who he phrased it as the deep ocean doesn't even know we're here yet. Like the ocean circulation is, ocean water will sink in the North Atlantic, and sometimes, it'll come out in the Pacific Northwest, maybe, 1,000 years later. And so what we've done, not even on geological timescales, but on just sort of even in the surface world is too rapid for these things. We're acidifying the oceans faster than they can turn over. So yeah, one of the breaks, sort of the maybe emergency breaks that saved the planet in the past, is that you put a lot of CO2 into the air from one of these volcanoes, and it happens over millennia. So the oceans are able to turn over. And you actually see this in a event 56 million years ago called the PETM, the Paleocene-Eocene thermal maximum, which some people have sort of worried or wondered why it wasn't a big mass extinction, because it is one of these big volcanic events. But by the age of mammals, you have this carpeting of carbonate shells on the seafloor that when the oceans turn over and they're more acidic, sort of dissolve them, and it's like an antacid that the ocean has to sort of curtail an acidification event, which might not have existed in the Permian. That might be one reason why the Permian was so bad. But what we're doing is too fast even for that to... if we were doing this over thousands of years, then maybe you'd have this. You might see something similar in the rock record, where you have this chalky sediment that turns to clay for 100,000 years, which is what you see in the PETM, this thing where it wasn't a major mass extinction, and the planet recovered from this big infusion of CO2, but didn't progress to a mass extinction. We're faster than that. So it's even that one isn't. It's not extreme enough for of an analog.
So I can see that you study this in extraordinary detail, and you can just kind of whip out factoids from, I could probably just say 75 million years ago, what happened? And you'd have an answer for me. But in closing, we were talking a little about modeling in the beginning, and that's kind of why you love going back in time. But in terms of, the accumulation of knowledge we've gotten over geologic time and geologic processes, there's tons of forecasting that sort of just seems to stop artificially at 2100. Do you geologists have like a sense that actually gets more accurate looking into timescales they're more familiar with, like rather than just looking at 2100 with lots of little micro uncertainties? If we're looking 5,000, 10,000, 100,000 years away, is there a lot of thought going into that, trying to project out with our geologic time knowledge?
I think people are just, rightfully so, more concerned with what's going to happen in the next few decades. And there it is. So like we are at, I don't know, almost 1.5 C above pre-industrial. So we have good reason to believe, based on paleoclimate studies and of the Greenland ice cap, that it probably doesn't like being there at 0.8 to 3.2 C above pre-industrial. So we might have already passed the point where Greenland just doesn't like to have an ice sheet anymore. The thing is, that takes thousands of years. And if you're worried about, your seafront property, you want to know how fast that happens. And so there are these processes that I would say the most urgent things that people are studying now is there's this one mechanism of ice sheet collapse called marine ice cliff instability, where if the ice sheets start disintegrating like this, where rather than just like sort of slowly melting into the ocean, they just become this like stack of dominoes that just falls. Then you are talking about differences in like tens of feet by 2100. So it's the over the long term, if we keep the temperature at what it is today, Greenland's all probably going to be gone within a few thousand years. But it's how fast is that going to be too fast to adapt? And I think a thing that like the mass extinctions show you is that sometimes it's sometimes it gets cold and things get wiped out. Sometimes it gets hot and things get wiped out. And it's really the pace of change if it's too fast for life to adapt. And given that there's ways of seeing sort of our global industrialized civilization as kind of like a superorganism-y thing, we don't know how adaptable it is to these changes. And so, it could be that we really derange the Earth system. It gets a lot warmer, but you don't get a big mass extinction. But maybe that surpasses the capacity for a networked global industrial civilization to stay upright. So there's so many uncertainties. I think the big lesson from geology is just that like you point at the rocks and you say, look, we know there's some unexpected surprises if you keep messing with this stuff. This is what it looks like in the worst case scenario. And it might be a little more uncertain than we think, which is a reason for extra caution, given that we're sort of taking this leap into the unknown, and we both don't fully understand how society and the economy works, I would argue, and what the relationship was with energy, I would say, and we don't really understand the solar system that we're pushing in ways that haven't been seen in hundreds of millions of years.
Okay, one last sort of closing question, and I'm not sure if you've given it much thought, but in talking about these kill mechanisms and means of sort of heading into disequilibrium, do you have any thoughts around geoengineering in terms of reversing some of these processes? Human beings being able to act at this incredible scale and again mimic these kill mechanisms, often just through our waste products and through, I guess, like an entropic flow. What are your thoughts about the potential for the reversing some of these processes by just the application of doing more work? Or is it on a conceptual level, is it too driven by needing the steroids to get the work done?
Well, so I think the people who you'll find who are most skeptical of geoengineering are sort of deep time geochemists. There are some advocates in that community as well. But sort of, if anything, the Earth history teaches you caution with stuff like this. Geoengineering is a very broad term that covers a lot of things. So like sulfate aerosols is one thing. I think there's things that are worrying about that, especially like we don't fully understand it. We don't really understand its impact on like monsoons and agricultural regions and stuff. And it could be this geopolitical nightmare. You'd have to keep doing it for thousands of years. What I think is kind of eerie is that in the big mass extinctions, at least, and maybe this is unfair to geoengineering, but it's at least sort of resonant that the things like the Siberian traps would have been putting out a ton of CO2. They also would have been putting out occasionally big pulses of sulfate aerosols and masking the effect of that warming. And it might be the termination shocks that are killing things in the mass extinctions. It might be that you get this pulse of sulfate aerosols that are masking the CO2 just billowing from these volcanoes. And then once those rain out, you jump 4 degrees C, which is kind of the worst case scenario for geoengineering as well. I know there's some very smart people studying this. I think it's good that we're studying it, like rather than just putting a lid on it. But we need to exercise a lot of caution. There's other ways of just dumping ground up basalt on agricultural fields and in the ocean is talked about, which is basically accelerating this rock weathering mechanism that I've been talking about that the Earth does on itself over 100,000 years, but that we kind of want to accelerate. There's reason, geochemically it all makes sense, but then you start breaking down the numbers and it's like we would have to grind up like gigatons of extra rock every year, ship it all over the planet, dump it in the ocean to take out a 40th of the annual emissions that we're putting out. So I think whenever you look into any of these, they're all sort of like just very marginal, and they seem like such a huge diversion of energy and talent and money that the number one thing we have to do is just stop putting CO2 into the air. Like that's the lever we should be trying to pull primarily. And it's good that people are studying these other things, but they're never going to account for the main problem in the room.
Well, I mean, it's wild. There's a geologist, and I may be misquoting him, but I think they were saying that human beings, through mining and blowing up aggregate, have an impact of moving more of that aggregate than all of Earth's weathering processes, whether it's streams
Yeah,
or winds.
yeah,
But we're doing that
right.
for economic reasons. And so a lot of these things require the enormous application of energy to do things that have no economic purpose other than maybe
Yeah,
averting
exactly.
catastrophe. So, okay, Peter, we're gonna have to leave it somewhere. I think that's a good place to leave it. Thank you so much for this backgrounder. I think it's great to sort of depoliticize some of the climate debate just by revisiting Earth's history and just getting a sense of how dynamic everything is, and maybe opens people's minds a little bit more to some of the experiments that we're conducting right now as this incredibly potent fire rate.
Yeah, well, thank you for having me. I hope I didn't get too wonky. I'm really deep in the weeds on this next book, and I'm over caffeinated, so I'm sure that was kind of an information avalanche. But thanks for having me on.
Well, yeah, thanks for the teaser in terms of the new book, and we'll look forward to having you back on when that comes out.
All right, great.
All the best.
Thanks so much, Chris.